All right, today we're talking about geometric probability. So it's always annoying because when we're doing geometry, it always ends up being an algebra problem. Like eventually we have to solve for variables. It might just be a huge equation bash. This time we're working from a different type of problem into a geometry problem. All right, so our agenda, that's all we're doing today. There's not much to talk about for this. The best way to learn it is to do problems. So I have a lot of those. And there's two cases that you'll see. One is that the problem is clearly geometry, and you're most likely like comparing the areas. So you're looking for the area of what's good, and then divide that by the area of like the total region you're looking across. And the other case is where you have to convert a non-geometry problem into a geometry problem. So for both, it's usually like good area over total area, the same way that probability is like what you're looking for over the total. And then for non-geometry problems, this is the typical problem you'll see in math cons or AMC. It's like people, they want to meet at a cafe, but they only stay for a certain amount of time. And they want to meet during this time interval. What's the probability that they meet? And we'll see one of those problems. But these can come in any shape, or I guess you'll see more of them in like AMC than Amy. For some reason today, the problems that I chose, a lot of them are from Amy, but they're like early level questions. So don't worry if you see the Amy format, they won't be too bad as long as you know like kind of how to get the problem set up. I feel like that's the hardest part. Okay. So you should have your handout, and I have the problems on this, so you can look along. So let's do the first one. I'll give you all a couple of minutes to work on that. Okay. So I'll draw what it's going to look like. First, we have a unit square S. So this is 1 on each side. And dp is the distance from a point P to the closest side of S. So let's see where all the points P are, where dp is 1/5. So the closest that P is to any side of S is 1/5, which means that this is 1/5. So there's like a border of 1/5 formed around this inner square. Right. So if I take any point on this square, like this one, then the closest distance is right there, and this is 1/5. If I take a corner, the closest distance is still 1/5, either that way, up or to the right. So I formed this inner square, and dp can only be greater than that. So right away, I know that the outer boundary isn't going to work. All right. Now it says dp is less than or equal to 1/3. So let's draw the square where dp is equal to 1/3. And that's right there. Again, same reasoning. Each point is 1/3 away from the closest edge. And now what we're looking for is the area inside the black square, but outside the brown square, because it's between 1/5 and 1/3. So our answer becomes the area of the black square minus area of the brown over the total area. Now it's important to keep in mind, like, what is the total area that we're dividing by? Well, it's the total area of S, which is 1 because it's a unit square. All right, so the area of the black square is, well, first off, the side length of the black square is 1 minus 1/5 minus 1/5, because I'm taking 2 chunks of 1/5 out of it. So this is equal to 3/5. So that area is 3/5 squared. Then the area of the brown square is 1 minus 2/3, or 1 minus 1/3 minus 1/3, which is 1/3. So this is minus 1/3 squared, and then all over 1. And simplifying, I get 9/25 minus 1/9, or 56/225. So my answer, since it was asking for m plus n, is 56 plus 225, which is 281. Okay, so this is an example of type A, where we know this problem is geometry straight away. And all we're doing is solving for the areas and then dividing. All right, we'll see examples of where they won't have, like, it won't clearly be geometry, but we can convert it into a geometry problem. All right, so let's try this one. I'll give y'all 3 or 4 minutes to do it. Okay, so I'll draw out the picture. Okay. So I've ignored the axes of the coordinate plane. I just put down the rectangle. And now we're looking for the area of all points where the probability that a point in this rectangle is closer to the origin than it is to 3, 1. So this is 3, 1. Now when we're like looking for the direct middle, so we want to separate this entire, like all of this into two parts. One that's closer to the origin, and then one that's closer to 3, 1. So to do that, I connect these 2 points, and then I take the perpendicular bisector. So I bisect that and at a right angle. You'll see why, like if I take any point along this line, then it's going to be the same distance between 0, 0 and 3, 1, because these two right triangles are the same. All right, so that's if I take a point along the line. And then if I take a point to the left of the line, like over here, then for sure it's going to be closer to 0, 0. And if I take a point right of this line, then it's going to be closer to 3, 1. So I want all the points to the left of the line because I want it to be closer to the origin. And now we're looking for probability, which means that we're trying to find the black area over the total area of the rectangle, which is 1 times 2, or 2. So how do we find the black area? Well, let's find the midpoint. So what is this point? Well, it's the midpoint of 0, 0 and 3, 1, which is the average. So I take the average for both 3 halves and 1 half. And then you may not know this, but actually or I did talk about it one lesson. The slope of a line is the y minus y over x minus x. So in this case, it's 1/3. And then since this line is perpendicular to it, the slope of that is negative 1 over 1/3, which is negative 3. And what does it mean that the slope is negative 3? It means that if I draw in this triangle, then the red side is 3 times the brown side. So that's what negative 3 means, having a slope of negative 3. I actually just realized I did not need to do that. So disregard what I just said. I suddenly forgot something. Notice that, like, let me draw this line in. I can actually move this triangle over. So it's like, so it actually becomes the same as a rectangle, this trapezoid. And we already know this point is 3 halves. So I'll just treat this like a rectangle because I can move that triangle part over. And now the bottom is 3 halves. The height is 1, so the area is 3 halves. And then divide that by 2, so it's 3/4. So I suddenly forgot about that. But just keep your eyes peeled for different ways to do it. So if I could have done the problem like pretty quickly still if I did that, but it would have taken like 2 minutes longer. A quick recap. So I drew a diagram. Oops. I drew a diagram of the rectangle. And then I found out what is the area that I'm looking for. So it's this area. And then at that point, it just becomes geometry. So finding this area divided by the total area that I can choose from. Okay. Let's try this one. Okay. Now, after reading the question, it doesn't seem like the number 2020 matters at all. So I'm just gonna ignore that. Okay. So I'll draw out a unit square. Let me just assume that this is 0, 0. This is 1, 0, 1, 1, 0, 1. And it says that the probability that a point is within d units of a lattice point is 1/2. A lattice point means a point where both coordinates are integers. So the only lattice points in this diagram are the corners of the square. The probability that the point is within d units. So if a point is within d units, for example, 1, 1, then it's within this circle, right? And this radius of the circle would be d. So any point that I choose within this circle is within d units from this lattice point, which is the center, but it can't be outside that. So I'm going to assume that d looks somewhat about like 1/3, between 1/3 and 1/2. And I'll draw the same shape for the other 4. Sorry, the other 3. Okay, now notice that this is a quarter circle a quarter of the circle with radius d centered at 1, 1. And then each of these are also quarter circles. Okay, now the probability is 1/2, and I find the probability by doing the area that I'm looking for. So the total area of the quarter circles, which is 4 times quarter circles, and then divided by the unit square, which has area 1. All right. And I didn't really talk about why I just ignored the 2020. So for each square, this is going to be the diagram, right? So each of those 2020 squares will have this diagram. So the probability won't be changed if I just assume that I'm looking at one square instead of a huge number of squares. Okay. Now the area of the 4 quarter circles is the area of one circle, which is pi r squared. So pi d squared over 1. Now solving for d, I get d squared equals 1 over 2 pi. Okay. And I know d is going to be less than 1 for sure, because the side length of the square is 1. So it's going to be like 0.4 around. If you drew a good diagram, then 0.4 would actually give you the answer. Otherwise, you can approximate what 1 over 2 pi is. So let me multiply both sides by 100. What is 100 over 2 pi? Well, 2 pi is around, so about 6.3. So this is about 16. Now square rooting both sides, I get 10d equals 4. So d is around 0.4. And it's pretty close to 0.4. Okay. So I'll go back through the process. I read the question. This time they gave us the probability instead of us having to look for it. And the area that's good, that's on the numerator, is the sum of these 4 quarter circles with radius d. And the total area that we're choosing from is the unit square, which has area 1. And this equals 1/2. And then solving for d using some approximations, I get d is 0.4. Okay. Now we finally reached a question that's not question A, it's a question B type. So it's not a geometry problem, but we can convert it into a geometry problem. So I'll give you all a couple minutes to try it out. Yeah, so let me explain some of the terms. A real number, of course, is any number, so it doesn't have to be an integer. Uniformly at random means that you choose a random number, like it's like completely random. So it's not like some numbers are more possible than others or more probable than others. And then independently means that one decision doesn't affect the other decision. All right. So what I'm going to do is draw a rectangle because I want to convert this to a geometry problem. So I'll say this is Chloe, Lawrence. And then let me put this on the coordinate plane. So assume that this is 0, 0. This is 4034, 0. This is 0, 2017. And this is 4034, 2017. So I've put a rectangle on the coordinate plane. And how does this help? Well, let me just choose any point within the rectangle. So let's say I chose 3000, 1500. All right, so this point represents Lauren choosing the number 3000 and then Chloe choosing the number 1500. So my y value or my x value is always going to represent Lauren's number, and then my y value always represents Chloe's number. Another example is if I chose this point right there, that just means that Lauren chose 4034 and Chloe chose 2017. All right. So I'll get rid of that. Now, how do I represent Lauren choosing a bigger number than Chloe? Well, again, Lauren is represented by X. So I can just basically say Lauren is X. And then Chloe is represented by the Y coordinate. So I'll just say that's Y. So I'm looking for all the points where X is bigger than Y. All right. And remember, we're actually on a coordinate plane. And I can actually graph this line. So first I treat it as X equals Y. And that line goes like that. So this is the line X equals Y. And then the line X is greater than Y is to the right of that line. So now I know that this slope is 1. And since 4034 is twice of 2017, then this is 1/4 of the area, and then this is 3/4 of the area. So my final answer is 3/4, because that's the area, that's the probability that this that the point is within this region. So a quick recap is that first off, this is the second type of problem that's not geometry, but we can convert it into a problem that's geometry. So I draw it. I could say the coordinate plane, but it doesn't have to be the coordinate plane. I could have just drawn a rectangle and then drawn this line in. But converting, putting it on the coordinate plane lets me like write down this equation, and then it makes more sense like why I'm drawing a line over here. So I treat Laurent as X and then Chloe as Y. And the problem says that I want Laurent to be bigger than Chloe, which means that X is bigger than Y, which corresponds to that region, which is 3/4. Okay. All right. This is our next one. So this is pretty similar. Try doing it the same way. But it's going to be a bit different because this time it's not a simple diagram just like that. Each person stays for a certain amount of time and m minutes. So it's not going to be a super trivial shape. It might be a weird diagram, but see if you can figure out what the diagram is going to look like. Just a quick note, this problem is an Amy problem. So like all that stuff on the bottom, m equals a minus b root c. You don't really have to worry about that. Like all of this here is just for formatting. All you're looking for is what m is. Okay. Now, what are the constraints? Well, they have to arrive between 9 and 10 a.m. both. Oops. So I'll draw out a square like before. And then this, so the left-right direction, I'll call this person A, and then the up-down direction, I'll call it person B. So like before, whatever the A value is, that's like what time the A person is going to get there. Whatever the X value is, that's what the time that A is going to get there. Whatever the Y value is, that's when B is going to get there. So I'll call this 9 a.m., that 10 a.m., and that also 10 a.m. Okay. So for example, if I choose a point in the middle, that means that A arrived at 9:30 and B also arrived at 9:30. If I choose a point out to the side, that means that A arrived at like 9:50 and then B arrived at 9:35 or something. So we can treat it like the coordinate plane, but I'm not like directly saying it is. Okay. Now, what else do we know? We know that they stay for m minutes. And this, again, we're given the probability is 2/5 or 40%. So we're looking for what m is. Well, we know the total area is 9 a.m. times 10 a.m. Or I mean, this side length times that side length. So I'll count this in minutes. This is 60 minutes or 1 hour. So I'll say that the total area is 60 times 60. All right, I prefer to work in minutes because I'm given that m is in minutes. And now all I have to know is, what is this? Or actually, I do know what this is, but how is this going to help me get what m is? So I can solve for the area that I'm supposed to get, and that area is 2/5 times 60 times 60, which is 1440. So the area of the region that I'm supposed to get is somehow supposed to be 1440, and I'm guessing that it's dependent on what m is. So at this point, if you know how to do it, then once you learn how to do it, basically, these problems become much simpler. But if you're just trying this out, then it might be a little hard to see. So my first step is going to be, well, let me assume that person A arrives at 9 a.m., which means that my x coordinate is along this line. All right, so let's assume that person A arrives at 9 a.m. and person A stays for m minutes. So person A is at the cafe from 9 to 9 m. And then for them to meet, that means that person B has to arrive between these 2 points, right? Otherwise, if person B arrives after 9 m, then there's no way they're going to meet at all. And now let me assume that m looks something like that. So this time is 9 m. And why is this important? Well, person B has to arrive within this interval. Okay, so when A is 9 a.m., then person B has to be between these 2 points. And something to keep in mind is that when I'm finding area, I can think of area as like the set of all points that work. And sometimes I can like think of area as the sum of all the lines that work. Like I can break it up into little lines. So now I'm breaking up the area that works into these little lines. Now let's do another time. So let's say person A arrives at like 9:05. So person A is here from 9:05 to 9:05 plus m. Which means, well, person B wants to meet person A. Person B can either arrive between this time, or person B can arrive at 9 a.m. And let's assume that 5 is less than m. Okay. So person B could arrive at 9 a.m., then wait m minutes. And then because they waited m minutes and m is bigger than 5, then they have a little overlap that looks something like this. So that's B, and then that's A. So my line that works is actually a little bigger this time because B can go from 9 a.m. up to 9:05 plus m. And then I'll assume that all of the times between 9:05 and 9 o'clock work the same way. So does this keep going like that? Well, is it just gonna end up being this area? Well, it shouldn't. First off, because that wouldn't make sense symmetrical wise. The second, because when I reach 9M, so I'm at the time 9M. Let's say person A arrives at 9M, and then when can person B arrive? Well, person B, actually, let me do 9M plus 1. Okay, so person A arrives at 9M plus 1, and then they stay for M minutes. So they leave at 2M plus 1. Person B has to either arrive between these two times, or they have to go at most M minutes before person's A arrival, so they intersect like that. So person B could either come at the latest 2M plus 1, or at the earliest, they can come at 9:01, right? Because if they came at 9:01 and they waited M minutes, then at the very end, when he's about to leave, then he's going to meet person A. All right, so we've just shown that 9 o'clock isn't actually going to work the whole time. So at this point, it actually goes a little above that. So it's going to look like that. And then I'll assume it works for all the times between 9M and 9M plus 1. So now my shape looks something like this. And then if you're a little lazy, then I can actually just draw out the rest of it like so, because I know it's going to be symmetrical. It should be symmetrical along this axis and along that axis. So it turns out that the area that I'm looking for is this shaded region. And another way you can think of this is like you can do it by counting the regions that don't work. For example, if I chose 9 a.m. for person A, then the times that don't work are from 9 a.m. to 10 a.m. And I could do the same process just for all the other ones. All right, so let me redraw this shape because we're really close to being done. All right, this side, this is M. This is 60 minutes. So this length is 60 minus M. All right. And I know that the shaded area that I'm looking for is equal to what I found earlier, 1440. So shaded equals 1440. But it's kind of hard to calculate the area of the shaded region. So I'm going to find the area of the unshaded. And the unshaded region is 3600 minus 1440, which is 2160. And how do I solve the area of the unshaded region? Well, first off, that shouldn't be shaded. So this, if I combine those two triangles, it looks like a square, and it is a square. So the square's area is the side squared, which is 60 minus M squared, and this equals 2160. All right, finally, all I have to do is solve this. So 60 minus M equals 2160 square rooted, which is 6 root 60, or 12 root 15. And then M equals 60 minus 12 root 15. So what does it ask for? A plus B plus C. So the answer turns out to be 87. I can box that. This was an Amy level question. But the only hard part here was actually just under like the first step. The hard part is like if you don't know how to do it. But once you know how to do it, and I hope hopefully you do, then you can just draw out this diagram because you know it's going to look like that. And then after that, as you can see, the steps were basically just solving for the length. So I think we have time for one more, and I want to get to it. Let's see, let's do this one. So that's this is our final question. Y'all can do the other two for home. Oh, we don't have homework. Well, you can do it for fun. All right, this is our last question. Let's take 2 or 3 minutes to do it. I'll go for it. Okay, for the sake of time, I'm just gonna get started. This one is a geometry problem. So I start off with the point where the frog is at. This is the frog. And the frog makes 3 jumps. So after the first jump, the frog can be anywhere along the circle. A circle with radius 1. So it has to be on the point or on a point on the circle. All right, it's not possible to go anywhere else. Then the frog has 2 more jumps to go. Now with these 2, I'm just going to think of it as 1 jump because the trick here is to notice that like within a circle of radius 2, if I try making 2 jumps of radius 1, then every point inside the circle is equally probable. If I chose like a point over here, then there's really only one way to get to it or 2 ways to get to it. I either go like that or I go like that. If I choose this point, I either go like that or I go like that. And then outer edges, there's only one way, but it doesn't really matter because there's infinitely many points in this circle and then each one is equally probable, as you can see. So it doesn't really matter that the outside edges or the outside edge only has one way to go to it. So with these last 2 jumps, let's say that the frog is here. The frog can end up anywhere within a 2 meter radius with equal probability. All right. And now this is essentially like this 2 meter radius circle is essentially like the area I'm choosing from. And then the area that I want is to end up back inside this circle because I want it to be no more than 1 meter from the start. So the final step is to find the ratio of the shaded area to the total area. which is 1/4 because the radius is half. So 1/4 is the answer, and it took a little bit of insight to be able to do it. All right, so this is actually our last class. Thank y'all so much for like being a part of this class. It was a really great experience for all of us as instructors. I'm not really sure how the poll works. Do y'all want the poll?
There's a poll?
Yeah, I didn't realize either before today.
Oh.
All right, I'm just gonna relaunch it. All right, if you want to answer it, go ahead. We don't have the test for this, but so you can just ignore that. We would really like feedback though. Again, so all the resources that we have are going to be on the website. For me, I know that I'll have all the slides and the handouts and the homework, the keys on the website. I won't have the solutions, but you can probably look up most of the solutions on AOPS.
Okay, so the units are 1 through 5. I don't know what units those are. Okay. I can just switch it up though. Yeah. I'll look through it right now.
Oh, sure.
Course and exam description. Okay. What the hell is this? What the? Okay, so Newton's law of motion, work, energy, and power to move the particle of linear momentum and rotation or on the exam, the oscillation.
So for some reason, if y'all like didn't know at all, and somehow just didn't ever.
Hold on. So what was oscillation?
This is where everything is. And of course, we have the videos. So let me see if oh no.
Oof. Just go on Flashmath. Or you can just hit the clash.
Oh, I didn't realize. I was always like, there's no back arrow. What's going on? Where is it? Yeah, so there's session recordings for every class. If you find it helpful to have like the problems worked out, then go ahead and check this. Yeah. Okay. So we were planning on like maybe having more of these classes, but we're not sure like exactly how this is going to work. Like, are we going to be doing math only? What level is it going to be? So this poll is really going to help us get a better understanding.
Input is appreciated.
Yep.
Oh, right.
If you have any individual questions or you just want to ask something, you can ask on the chat. Let me just open it up real quick.
But not represented. If you come to the open on College Board. Whatever. Now where the heck? Where the phone better?
Isabella, do you know the other instructors, like their names?
Wait, for what? For this or what?
Oh, like potentially for Yusuko.
For like aces?
Oh, for this. I meant like.
I have no idea.
Okay. Yeah, I don't know. Oh yeah. Yeah, y'all can leave. Again, thank y'all so much for doing this.
Yeah,
with
thank
us.
you guys for everything. It's been so much fun. Hope you guys learned
Okay.
something new.
Yeah, we're probably
Bye.
gonna visit very soon. All right, I guess now. Bye, y'all.